as a cosmology. And he's currently studying the motion of these dwarfs through the intergalactic medium using radio observations and fluid simulations. Okay. So he's going to be telling us about the intergalactic medium, which is half of the gaseous gas, and is expected to. Well, I don't want to infringe too much. Et pour ceux qui ne sont pas là pour écouter la présentation, si vous écoutez assez de ne pas parler trop fort, ça sera très très bien affiché. Okay, you can't hear at all. I think it's my microphone techniques. Okay, d'accord, on commence. So if you can invite Neel with a round of applause.
I sometimes speak really quickly, so if in case I am not really coherent, let me know. Alright, so I just am. I first wanted to talk about a galaxy which is undergoing RAM process stripping, so that I could link it to what Ashia presented to us and connect it to jellyfish galaxies. However, the more and more I read about jellyfish galaxies and the system which I was studying, I found out some really weird things about just plain old gas in the universe. So this essentially is going to be the exploration which I went through over the past 2 weeks of the state of gas in the universe, and I'm going to try to weave like a coherent story of where exactly the gas is and what is it doing all over the universe, everywhere. Okay, so let's meet the protagonist of our story, and the protagonist of the story is good old hydrogen. Hydrogen is the simplest element in the universe. It is simple because it is just made up of two very basic things: a positively charged proton and a negatively charged electron. These positively and negatively charged, they attract each other, and that's found. The physics behind it is complicated. We need not go into it. The entire story which I'm about to tell you can be understood just through the fact that positive and negative charges attract each other and they can be bound. When such individual hydrogen is found in the universe, just alone itself, it's called neutral hydrogen because the charges cancel out, there's no charge, it's neutral. When two of these atoms essentially join up, we call it molecular hydrogen. Well, the electron and the proton can be bound at different energies. If you provide some extra energy to the electron, it can essentially be slightly farther away from the proton, and you can provide this extra energy by just shining some light on a particular object, any object. So, for example, my shirt, it is actually a glow-in-the-dark shirt. If you shine light on it, it absorbs the light. So, for example, if I just shine the spectrum which Ashia was showing us, onto hydrogen, a part of it will disappear. Here are the red, here in the cyan, multiple lines of purple. Similarly, my shirt right now, in all of this light, is currently absorbing this green light. You don't see it, but if you turn all the light off, my shirt will start emitting a green light, and you will start seeing green, quite like over here. So every single material can absorb particular frequencies of light, and every single material can emit particular frequencies of light, and this is hydrogen. This is essentially what hydrogen does. Every single line you see here is a different energy level. This is very low energy towards the violet and ultraviolet. They are very high energies, and this is what you see. Hydrogen can be bound to the electron, essentially stuck to the electron at these various energy levels. If you give it some red light, it will be bound at a lower energy level. If you give it more energy, it will be bound at a higher energy level. Okay. What happens if I give it a lot of energy? You just hit it really hard. Well, you can just knock the electron out. You can just have a bunch of gas where the electrons are not bound to the protons. The gas has so much energy that all the electrons have been blown apart, and now you just have a goop of unbound electrons and protons. We call it plasma. You might have heard the word plasma before. That's what plasma is in the context of physics. Okay, so I have given you like a very quick introduction to various things hydrogen does. It can be just lonely and alone, just a proton and an electron. We call that neutral hydrogen. It can be bound together to another hydrogen atom. We call it molecular hydrogen. It can jump up and down in these various energy states, which gives us the spectrum, and the spectrum which Asha was showing us. And if I give it a lot of energy and bump it out, bump the electron out, you can also get a plasma from hydrogen. Okay, so that's our protagonist. I introduced our protagonist. So if a story has a protagonist, it usually also has an antagonist, and the antagonist is also hydrogen. There could be other characters in the story. The romance interest is also hydrogen. The NPC in the story is also hydrogen. Essentially, what I'm trying to say here is it is and it was all hydrogen. You and I and the stable, what I was drinking, the projector, everything was once hydrogen or sometimes helium. This is for the physicists. Sometimes helium is for the physicists because they complain often. All matter in this universe was once hydrogen. Through various processes, like forming stars, dying stars, bumping stars, essentially stars doing their things. Stars are engines and factories to convert hydrogen into n number of other things. All the carbon which you see in your body, in plants, it comes from in the core of stars. All the gold, some of you might be wearing on you, it came from when stars blew apart. But all of it has its origins in hydrogen, the very simple atom whose almost entire physics I explained to you a while ago. And yeah, you can call the story of the universe essentially the sonata of hydrogen. This is a superb science fiction novel. I missed the T here, but the star is, I guess, is kind of appropriate. But it's a lovely science fiction story called The Hydrogen Sonata by Ian M. Banks. It's a part of the culture novels. Don't start with this book. Start with Consider Flowers. It's a beautiful novel. Anyway, we kind of know where hydrogen came from. We as physicists, astronomers, we know the origins of hydrogen, but we don't really know where it is today. What do I mean by this? Sorry. So we kind of know where all the hydrogen in the universe came from, where it came from, but we don't really know where it is. And let's see where we see hydrogen these days. Okay. This is again going to be something which is going to offend a lot of physicists in the room, but I'm going to try. So at the start of our universe, the universe was in a very, very hot, dense state, and it was essentially plasma, the kind of plasma which I showed you. There were a bunch of protons and there were a bunch of electrons, and they had a lot of energy, and they couldn't stay bound. You couldn't form neutral hydrogen. You could not form a molecular hydrogen. They were just bumping around into each other, not forming any kind of gas per se. And for weird reasons which I won't get into, the universe expanded. Well, a weird thing happens when you give gas a lot of space. I have a can of gas here with me right now. Okay? This has a bunch of gas in it and some perfume. If I let the gas go, it goes out. It just wants to expand out. If you compress gas and give it a bunch of space, it just wants to go out. It just wants to move. Well, once this happens, you give the gas more space to be. Once this happens, you give the gas more space to be, and the gas cools down. If you want to play around this right now, you can just take this can and blow some on your hand, and you feel intensely cold. You can actually take a glass of water and blow this compressed gas on it for like 5 minutes, and you can actually freeze the water. So essentially, if you let gas expand, it cools. You can play around with it. You can pass it down if you want. So if you want to, you can try it out. Just expand the gas and feel it cool. So all this plasma in the universe essentially cooled down once it was given a lot of space. Well, I'm going to play a couple of videos for you right now. Unfortunately, they're not embedded in the video, so I have to go open the gist from there. But I'll try my best. Yes. Not good. as it expanded, or regions of the universe as they expanded. Okay. So here at 0, essentially consider this to be when the Big Bang happened, and this is just as how the universe evolved. As you see, baryons, which are essentially the protons and electrons, which I talked about in the context of hydrogen, were bound to the photons for a very, very long time. As the universe's radius, kind of, if I may use the word, grew larger and larger, the photons and the baryons kind of decoupled. They kind of moved away from each other. Here's the point at which you can see the photons and the baryons decoupling. So the universe expands, and the photons move away from the baryons. And because the universe is now cooled, the electrons fall into the protons and they make good old hydrogen. This is where hydrogen came from. Hydrogen, all hydrogen in the universe, essentially just directly came from the Big Bang. There was some helium as well, and very tiny amounts of lithium, but we don't need to get into that right now. This is the same GIF, but in 2 dimensions. At the start of the GIF, you will see kind of a yellow light, and the yellow light splits into red and green. The red was the baryons, and the green was all the photons. So the photons have escaped and have left all the matter behind. That's correct. If you give me a second. If you take a bunch of these, essentially points expanding gas, you get kind of a weird feature. If I take a bunch of these blobs of gas, which are expanding in all directions, and I kind of overlap them on top of each other, you get kind of a random noise-like structure. Astronomers out here might have seen a similar structure in some images which are very famous. Give me a second. So those various expanding points which I showed you, which made a random map, is essentially this. This is called the cosmic microwave background. This is essentially all the photons which escape the hydrogen which was formed. The hydrogen, is it better? So hydrogen formed and it let a bunch of light out. All the light escaped, and we use some very, very sensitive telescopes which can detect microwaves to essentially find this pattern on the sky, this scatter of light on the sky. This is essentially the entire sky, kind of like projected in the way you might have seen maps like this. So this is just anywhere on the earth, if you look up and project the entire sky, you will essentially find microwave light at a particular frequency which is distributed just like this. And all of this is essentially light from the first ever atom of hydrogen ever formed. And we see it, and physicists study it. So what this tells us is this is a signature of all the hydrogen that was ever formed in the universe. This is essentially letting us state how much hydrogen there is in the universe. Okay? And then we go about telling a story of the universe. All the hydrogen was formed here, all the light that's out, this entire region and this entire period in the universe from about 400,000 years ago to about 0.1 billion years. This entire period is where you just have gaseous hydrogen and absolutely nothing else. Hydrogen, just being mass, just it having mass, it collapses, and collapsing hydrogen makes stars, it makes galaxies, and that happens over here in the history and evolution of the universe. And stars and galaxies ionize hydrogen again. Well, there was a period where the universe was sparse that you could have this atomic hydrogen, but once you start forming stars and galaxies, you're compressing hydrogen again due to gravity, due to galaxies, and hydrogen becomes a plasma. So now, slowly hydrogen starts off in a neutral phase, into kind of being a plasma. Okay. So where is the hydrogen today? Well, most of the hydrogen today has, a lot of the hydrogen today, most is wrong word. A lot of the hydrogen today has formed stars, and this is M31. This is a galaxy very close to this is the closest galaxy to our Milky Way, and this is in the visible spectrum, very similar to the pictures which I showed you. And all of these are stars in this and a lot of hydrogen has actually converted itself into stars, and that's what we see. If we look at the galaxy in the radio, you see the gas in the galaxy. So complementarily, we see all the stars and we see all the gas. That is where we, on first principles, expect all the hydrogen to be. So if I just try to map out every single galaxy which we have ever observed, which is using the Sloan digital sky survey, using a telescope, we just map the galaxy every single night, map many galaxies by observing the sky every single night. You essentially get a web of these galaxies which emanate from the center of this particular diagram where Earth is, and every single little point over here is one galaxy. So we roughly kind of now statistically can say how many stars and gas have been converted into hydrogen. Where hydrogen is, if we technically add up everything you see over here, you should be able to retrieve all the hydrogen which you saw from the CMP. So if this is 100% of the hydrogen, if you add up all the hydrogen in gas and stars, you should be able to get, or you should be able to recover 100% of the hydrogen. But that is not the case. We only see 10% of the hydrogen in galaxies and stars. So where is the rest of that? Well, Ashia told us something very, very interesting. That galaxies are embedded in these gaseous halos, and these halos are called circumgalactic media. Circum being around, galactic being around the galaxy. So galaxies breathe gas, they take gas in, they throw gas out by supernovas and jets from the central black hole, and they cycle gas, they recycle gas over and over again. And using telescopes like Hubble, you can actually detect the circumgalactic medium around some galaxies. Okay. So the gas is okay. So now the story is that the gas is converted into stars. There is some neutral gas, and there's also gas around the galaxy. Okay. So if I kind of do statistics again and add up all this gas around the circumgalactic medium, how much gas do we have? About 20%. We only have about 20% at the moment. We only know of only 20% of all the gas in the universe. We haven't been able to see where the rest is. Well, we can use Ashia's pointers and investigate more. This is the coma cluster, also this is the bullet cluster, and here in pink you see heated gas. Essentially, using the Chandra X-ray observatory, you just point the observatory at a particular galactic cluster, and you will see a bunch of hot gas. And this is an empty cluster. In all the clusters which Ashia showed us, you had this hot gas which was visible using Chandra. And we expect this to be in every single cluster. There are clusters everywhere in the sky. Okay, so if we statistically add up all the hot gas in every single cluster and compare it to how much gas essentially the Big Bang theory tells us there should be, how much gas we find? Only about 24%. So we are now slowly counting up. We are doing a census of where all the gas in the universe is supposed to be. And as Ashia told us, clusters are the largest structures in the universe. They connect to each other and essentially form the filaments and the entire large-scale structure. So where is all the gas? And it is a very, very important question. Did someone just take all the gas and kill it and bury gaseous body in the forest something? Well, I started this talk by essentially calling it the gaseous beam, and as if I was just going to talk about gas here. Actually, it's kind of a mystery. It's a murder mystery of where all the gas went. Because this is gas which astronomers straight up have not been able to observe. We expect this gas to be out there, but we don't see it. Mind you, a lot of you might have heard about dark matter, or dark energy and other things which we observe. This is not that. This is just good old-fashioned hydrogen, which we simply have not observed and have not been able to account. So essentially, if you want to trace the history of hydrogen, you have to solve the mystery of the missing gas. And well, let's attempt to kind of try and do that. Okay. Oh, I have to show you the video. So I alluded to perhaps some of the gas being murdered and burned in the forest. It's kind of this essentially is a quasar. Quasar is an accreting supermassive black hole. It is at the centers of galaxies. Asha introduced us to supermassive black holes at centers. This is exactly one of them. And quasars are broadband emitters. They emit light in all frequencies. If you were to stand in front of a quasar, and if you were to take a spectrum of a quasar, this is kind of how the spectrum would look like. You stood right in front of it. But you are not in front of it, you are far away from it, over there at other corners of the universe, and the light from the quasar has to travel through the medium, whatever the medium is. And light travels through it. And you'll see that the gas between us and the quasar absorbs this light, and this light is redshifted, and you'll see multiple lines of light which are in absorption. So what this particular diagram is tracing are various clouds of gas which are absorbing some of the light and imprinting its presence onto the spectrum. And this forest of spectral lines is called the Lyman alpha forest. And this is called as the Lyman alpha forest. Lyman because that is just the hydrogen transition. It's called Lyman transition. Doesn't matter what it's called, which you saw being observed. And there's the Lyman alpha forest, and all the gas between quasars and us account for all the gas in the universe. No, it doesn't. If you add up all the gas traced by these quasars, if you see all across the sky, it accounts to only about 40 to 50% of all the gas. Okay, so if it isn't gas inside galaxies, if it isn't gas between clusters, if it isn't the gas between us and distant quasars, which are the objects which are most farthest away from us, where exactly is this gas supposed to be? Black holes don't accrete fast enough to essentially eat up all the gas. It simply is currently invisible. And this is a kind of dark force in astrophysics, because we don't really know where this gas is. We expect it to be in the IGN, which is the medium which the Lyman alpha force is tracked. But we have not actually seen it. Though we try to study dark matter, and dark energy, the invisible theoretical forms of energy and matter, just good old-fashioned hydrogen, half of it from the expectations of the Big Bang theory is completely missing. So, where is it? The quest to solve the mystery of the missing baryons is called the missing baryons paradigm, or the missing baryons problem. Baryons here is essentially just like a placeholder word for hydrogen. Theoretical simulations kind of tell us that this missing hydrogen should be in these beads, in these threads of clusters. So this is kind of a cluster, this is another cluster, kind of like in the images which Asha showed us, and connecting these are supposed to be filaments. Filaments which we haven't directly observed till literally a week ago, by the way. I'll show you some images of some filaments which you observed from observations literally which were published like a week ago. A bunch of these gas is theoretically expected to be in the filaments. Simulations of the universe tell us that it should should be there, but we haven't seen it. There is very tenuous evidence of it actually being, all of it actually being in the filaments. Okay. So how do we exactly go out in the filaments, which are far off from these clusters, and study the properties of this hydrogen gas, which we don't actually see? I completely forgot that this exists. This is all the gas which you don't see. It's supposed to be in the hot intergalactic medium. This is the cold intergalactic gas, the one which is buried, whose bodies are buried in the Lyman alpha forest. This is the hot gas clusters is the one Garcia showed us, and gas stars and the cold gases from radio images, which I showed you earlier. And this is essentially almost all of the missing gas, which we have not observed. Okay. So how do you observe this? How do you try to at least understand its presence? If you can't directly see any light from it, maybe you can dynamically try to understand it by figuring out what interacts with it. So these are jets from a black hole. This is a galaxy. At the center of the galaxy, a supermassive black hole. It's accreting a lot of gas. It's killing stars. It's stopping star formation, as Asha told us. And these black holes are burping out a bunch of these electrons and other matter out from the galaxy. Here in pink, you see the CGM, the gas that surrounds the galaxy. So as you can see, these jets actually penetrate through the CGM out into the IgM. So these jets interact with the IgM itself, whose density we don't know and where this missing gas actually is. So if we are able to kind of figure out how much these jets expand out in the medium, in a similar way, say, you can understand how this jet spray expands. It's actually very similar in structure if you observe it. You can probe the medium on the sides, and that's what people do. People try to figure out how these jets bend out in the IgM and figure out how dense the gas around it might be. That is one way to do it. You need to observe a lot of these agent jets everywhere, interacting with the IgM and see in which direction they bend to kind of probe how and where the IgM is flowing, where the filaments are. That's one, observing AGN jets. The other way, well, it's kind of interesting. A tangent for like about 30 seconds. You might have seen images like this before, where white light is shone on a prism, and a prism kind of separates the light into its constituent frequencies of light. So different frequencies of light, as you see here, are separated separated at different angles. You can see purple and blue over here, red over here. This happens not just for visible light, but if you were to shine, say, radio light at the prism, radio light also would split in higher and lower frequencies if it were traveling through a prism. The IgM, the medium between us and the quasar or any other faraway object, is also like a medium through which light travels. Different frequencies of light travel at different velocities in the IgM, which essentially lets us probe how the light will, when exactly the light will reach us. Essentially, you can use the entire space between us and a faraway quasar or a faraway object, like a prism, to see how light essentially splits. But firstly, you need white light source. Fast radio bursts. Fast radio bursts are essentially like laser pointers which are shown into the prism of the IgM. They're essentially explosions which we don't really know why they exist and where they come from, but they are just explosions which we really don't understand out in the universe, which are extragalactic coordinates. They happen in galaxies far, far away, and they emit a lot of radio light with a lot of energy. This radio light is not at a particular frequency. It's a mix of various frequencies. And the IgM acts like a prism and splits this radio light into its constituent frequencies, and you essentially use the IgM like a prism and figure out how dense the medium between you and the faraway fast radio burst is. So essentially using the IgM, using the medium between you and the faraway quasar like a prism, you are able to figure out how much material, how much gas there is. And one final kind of nail in the coffin like a thing, where people have tried to image the IGM directly. This is a paper literally from a week ago, a few weeks ago, where they use EOSITA, which is an X-ray observatory, to image a filament of the IGM directly between two clusters. This is cluster A3667 and that's A3651, and you're able to see the filament of gas connecting these two clusters, and that is where they expect that's where they expect the missing gas to be. However, this is just one cluster. Fast radio bursts are just we have only observed a handful of fast radio bursts, and we only observed a handful of these filaments. They don't account for all the missing hydrogen gas out there. So a lot of people think that this essentially solves the missing baryon problem. It's in the filaments. That's where the gas is. We see the hydrogen in between a few of these filaments, and that's where it's supposed to be. And people say that it is kind of the nail in the coffin of where it's hydrogen is supposed to be. This is just the Wikipedia page of the missing baryons problem, and it is written in a really weird way, which kind of tells you how much of this problem is actually unsolved. So, in general, the missing baryon problem is a major unsolved problem in physics. Various scientists have proposed explanations, but now have received acceptance as a widely addressed issue. This is a very weird scientist. A scientist organization that did solve it to satisfaction of others would surely win many prestigious prizes. It's as if this particular citation over here is trying to win a prestigious prize. And they talk about many claimed resolutions of the missing baryon problems using various probes of astrophysics, and claimed resolution also has a section called current state, which also says that a problem has been resolved, but here it says a problem has not been resolved. So there's a lot of debate in the scientific community of where and how the IGM is. And essentially that's about it. And right now, I connected to my work. So along with my supervisors, I'm studying this galaxy called WLM. It's a galaxy in our local group, so it's not actually very far away. And it is undergoing RAM pressure stripping, quite like the jellyfish galaxies which Ashiya showed us. However, it is not a part of a cluster. It is out there and as an isolated galaxy in the medium. It's undergoing RAM pressure stripping by the IGM itself. So I'm trying to use this galaxy as a probe for the density of the IGM in the local medium. And that's about it. We need more people to study the IGM because if you can't account for the baryon budget, if you can't recover all the hydrogen which was formed during the Big Bang, it's a major unsolved problem in physics and a probe for cosmology itself. Thank you. Kind of a tangent. I have some postcards and stickers here. If you just want some, take them. They have pictures of astronomical bodies, stars, and galaxies. They're here for you to take. Just come and pick them up.
Do you have some questions? Maybe I can bring a base up for some question.
Why do we observe stripping of WLM by IGM but not for other galaxies?
We don't really know because there is no probe for the IGM in the local group. The local group is supposed to not have a lot of gas. So if you point an X-ray telescope, say around a WLM, you don't see it because the IGM there is not. If the IGM is around WLM, it's not actually warm enough to actually come up in Chandra data. The only place where you see it is if you observe it directly in the 21 centimeter line is and that's what you see over here in this image. This is observed in this is essentially just neutral hydrogen. This is just hydrogen gas being stripped. If you use a radio telescope, you are able to see it. But this stripping is taking place due to this galaxy is bumping into the IGM and undergoing RAM pressure. And we are using the dynamics of how this galaxy changes to kind of prove where the IGM is. So we don't know why is it there or something.
More questions?
Take 1 second.
When you talk about I didn't hear it at the beginning. Where is the initial gas come from? The initial gas of the total gas. Because they were talking about percentage.
Yes. Okay. So this is essentially the evidence for initial gas. This particular image is just an image of the entire sky taken at a very particular frequency of light, and essentially, for all intents and purposes, without getting into nitty-gritty details, this is tracing the distribution of initial distribution of hydrogen all across the universe. This is all the hydrogen that ever was. Back when the universe formed, right now we can't account for it.
If you answered this question, would it somewhat clarify like dark matter?
Excellent question. Okay. So, one of the reasons why it is very, very important to resolve, quote-unquote, the missing baryon problems in context of dark matter is because a lot of these missing baryons they interact with galaxies. The gas from the IgM falls onto these galaxies and it changes the dynamics of the galaxy itself. And quite like WLM, the galaxy which I am studying, if the IgM is able to change the dynamics of the galaxies itself, one of the major probes for dark matter in the universe is the rotation curves of the galaxies. So, if external gas is perturbing internal gas, if you don't really know how much gas is out there, you can't really comment on how much dark matter there is in the galaxy itself. So, you really need to account for all the gas around the galaxy, otherwise you are getting wrong rotation curves, you are wrongly assuming the quantity of dark matter in the universe.
More questions? If not, then maybe I have a question. If you wanted to find all this gas and you had an unlimited budget, what instrument would you make? What telescope?
Okay, so the question is, if I had infinite resources, what instrument or telescope I would make to detect all the IgM that there is? Well, for starters, we can stop the current X-ray observatories from being defunded. For example, right now NASA is trying to just cut off all the budget for the Chandra X-ray observatory, which is used to study the IgM. So we need more X-ray telescopes and make sure that the ones which we have currently right now stay functional. Another one might be something like a Gaia, but so Gaia essentially is a satellite which tracks motions of stars in the Milky Way as well as in neighboring galaxies. So if you have a satellite like Gaia, which is slightly away from the Milky Way, which is like a very hard thing to do, you might be able to track and trace the motions of stars in nearby galaxies much more accurately, and you will be able to estimate the amount of gas they have, from which we can statistically kind of infer how they are interacting with the IgM. It's kind of a far-fetched idea, but it's something which I'll be currently discussing. A better bias.
Thank you very much once again.
Thank you, Neel, for the great talk. So thank you everyone for tuning and asking questions. Really appreciate it. Our next event will be next month. I want to make it happen that it will be then we will keep you posted on when that happens. Thank you and have a good night.